All right, so let's take a, different approach to solving. So we just talked about how we can maybe solve these polynomial inequalities by looking at a graph and trying to identify where the function itself, in this case, this parabola, has values greater than 13, right? So using a graph, pretty straightforward, all right? But I did mention at the beginning of that solving inequalities, when you're talking about linear inequalities, we solve linear inequalities just like we solve equations, right? So if you had something that was 3x minus 5 is greater than 7, right? You wouldn't take any different approach to this than you would have if there was an equal sign here, right? Uh, so you add 5 to both sides, and then, sorry, look at that. I even wrote the equal sign. Add 5 to both sides and divide by 3. You get your solution. Now, your solution is a solution set of values as opposed to just one number, okay? But in inequalities for polynomials, take that same idea where we're saying it doesn't matter that this is an inequality symbol when we're solving, okay? How would you solve a quadratic equation, right? Most of the time when we're solving quadratic equations, we have to set them first equal to 0. This is not going to be equal to 0, right? Oops, sorry about that. That's going to be a minus 3. It's not going to be equal to 0. It's going to be greater than or equal to 0. And what we've been working on in this unit is finding zeros, right? And finding zeros is the same process here as it is if this was an equal sign, right? Because the zeros of this equation are the values of x that meet this condition. So all we did was we rewrite this, right? We're not solving a different inequality right now. So the solutions to this inequality are the solutions to this inequality, okay? And the solutions to this inequality involve the zeros of the function. And when we find the zeros of the function, or how do we find the zeros of the function? When it's quadratic, we can use a quadratic formula or we can factor, okay? So if we factor this into these binomials and we start looking for the magic mix, okay, of the numbers that go here, we end up with a -3 in this place and a 1 in this place. Okay, so if we take this same approach, now here's where things get a little different. Okay, and what comes into play are a couple of other ideas, right? When we're talking about the degree of the function. Okay, when we're talking about end behavior and degree and end behavior. All right, along with the leading coefficient, all of these concepts that have been involved in this entire unit, right? Just having an overall understanding of polynomials, they're going to help us solve this inequality without a graph, okay? We still want to have knowledge of what that graph looks like, but we don't necessarily need that graph at that point, okay? So let's take a look. The quote-unquote zero that we would get from this. Now, here's what we're not going to do. We're not going to take this and say, where is this greater than 0, okay? We're not going to be looking at separating this into different inequalities. At this point, we just want to know what's the 0 from this part, from this binomial, right? So we add 3, we divide by 2, we get 1.5. Okay, I'm sorry. This is supposed to be a plus. This is supposed to be a minus. You guys get me. I make mistakes, right? So that's a plus. So this is a minus. And then over here we get x minus 1. Where does that equal 0? That equals 0 at 1. Okay? So now when we look at these values, these are the two values where this function crosses the x-axis. Okay? What are we looking for? We're looking for where this function is greater than or above the x-axis. So just knowing what we know about polynomial functions, knowing what we know about degree, about leading coefficients, and about end behavior, we know that this polynomial has end behavior that looks like that. Okay, right? It has mirrored end behavior, rising to the left and rising to the right. And we know that if this graph rises to the left and rises to the right, and it crosses the x-axis here and here, what we do, okay, is we separate the entire domain of the function into intervals. So we have the one interval that goes from -infinity to -1.5. Okay, and I'm going to use a parenthesis here. Don't be confused by the fact that I'm using this parenthesis. Okay, and then we have from -1.5 to 1, and then we have a third interval from 1 to +infinity. So when you think about what this graph looks like, okay, from negative infinity to its first intercept point. Now, if we did have the graph here, okay, we would have something that looks like this, right? This is the first intercept at negative 1.5. This is the first, or the second intercept at 1. So if we look at this graph in 3 different intervals, we have this first interval, which is from negative infinity to 1.5. We have this second interval, which is from negative 1.5 to 1. And then we have the third interval, which is from 1 to positive infinity. Okay. Where, under which of these 3 intervals is this function greater than 0? Okay. Now, what we do is, again, think about the graph. We know it's greater than 0 in here. Okay. But for the sake of only doing this algebraically, like I kind of cheated by even drawing a sketch of the graph. And I don't want to say cheated because we want to be problem solvers. We want to use different methods. Okay. But what we do is we find these zeros and then we take the domain, and the domain of a polynomial function is always going to be from negative infinity to infinity, right? So we take that entire domain and we chop it up using the zeros as beginning and or ending and beginning points of these intervals. Now pick a number that falls in this interval. Okay, you could say -2. All right, you could say -5. All right, what I'm going to say is -1 million, and I'm just going to use -1 million real quick because mental math wise. All right. Now again, you can look at the original inequality or you can look at this inequality. But if you rewind about 5 minutes ago, I said solving this is the same as solving this. Okay. Now, if I put -1 million into this function right here, all right, what's going to happen? I'm not interested in the actual value here. Let's just use our intuition, our brain power, our mental math to figure this out. If I put -1 million in for this value of x and I square it, what is that? That's an incredibly massive positive number because -1 million squared becomes positive. Negative times a negative is positive. Then we multiply that massively huge number times 2. And then we subtract 1 million, and then we subtract 3. What's the overall value of that number? Massively positive, subtract a million, okay, then subtract 3. But because of this term, because it's massively positive, these are insignificant. It's going to be greater than 0. So if I plug -1 million into this function, it's definitely greater than 0. So this interval is a part of my solution set. Let's do the same thing here. Tell me an easy number to work with between -1.5 and 1. How about 0? Right? Plugging in 0 is easy. So let's plug in 0. What happens if I plug in 0 here? This whole thing becomes 0. What happens if I plug in a 0 here? This whole thing becomes 0. So I've got 0 plus 0 minus 3. What is that? That's definitely not greater than 0, right? That's equal to -3, which is not greater than 0. So we're not using any points in this interval. I only need to test one of them, okay? Any point in this interval is going to produce values because again, these are the zeros, right? The graph either goes below the x-axis between these two zeros or it goes above the x-axis between these two zeros. We already know based on all this stuff, right? The end behavior and all that, what's happening. But if we didn't, we know that it has to dip below or it has to go above the x-axis at that point. And then last but not least, if we plug in +1 million, again, I can plug in any number I want. I could plug in 2. That would be fine. Okay. If your mental math is good with 2, use 2. But I'm going to plug in +1 million here. I'm going to square it, which is going to, again, massively huge. Then I'm going to double it, even bigger. Then I'm going to add a million and I'm going to subtract 3. Is that value greater than 0? Yes, indeed it is. This is also greater than 0. So check mark. So the intervals that have the check mark where I test a point in each one of these intervals, okay, the intervals that have that check mark are the intervals of my solution set. So I'm going from -infinity to -1.5. And now is when I know I wrote a parenthesis here, okay? I couldn't use a bracket here and a bracket here, okay? So when I'm done, I have to say, am I allowed to include this? And all it comes down to is Do I use a bracket or parenthesis? It's all about this right here. If we can include it, then yes, we use a bracket around that. We don't use brackets around infinity ever, right? Okay. But we do use brackets around numbers if we want to include them. So this becomes our solution set to this polynomial inequality. So again, it's really a three-step process. Okay. Find the zeros. You can do that algebraically. Step 2, write the intervals. Write all of the intervals in the domain separated by these zeros, okay? And then test numbers in the intervals. This is our three-step process for solving polynomial inequalities, okay? Let's practice some more.